Welcome friends. In our last session, we started discussions about pricing systems, that how by appropriate pricing we can also maximize our revenue. We discussed different scenarios that you may have replenishment of the stocks, without replenishments also there are certain situations. So, in that case everywhere we saw that deterministic and stochastic situations are possible. In this particular session, we are going to discuss a particular scenario which is very much similar to the cases which we were discussing when we were talking of allocation of the capacity. This is a situation of single product dynamic pricing without replenishment. So, here we will discuss the mathematical formulation of such type of scenario, and with the help of one example also we will like to see that how such cases are handled. As we already explained that there are a lot of such situations where this single product dynamic pricing without replenishment is applicable. We have, for example, flights where you have very much application of dynamic pricing, there is no possibility of replenishment, and you have a single product like these days the entire flight is economy class flight. So, that is economy class, no replenishment is possible. This is a very classical case for this particular type of scenario. There may be other cases which are similar to that. We discuss in operations management, inventory management courses a very popular type of inventory management model, that is news vendor model. That news vendor model is also similar to that. The only thing is that in this news vendor problem, we generally do not apply the concept of dynamic pricing, but you can think of a situation that dynamic pricing may be applied, that if you have a very specific type of newspaper where only some limited copies are available, and you may charge to the customer as per the availability of the copies. In the beginning, when you have, let us say 50 copies, you are charging 10 rupees per copy, but after 25 copies you still expect more than 25 customers are possible to buy these newspapers, you may increase the price from 10 rupees to 12 rupees. So, something of that sort is possible in newspaper case also. So, there are variety of examples of this scenario, and you may also like to add more number of scenarios for this single product dynamic pricing without replenishment case. Now, in this case, when we want to develop a mathematical model, we are considering only a single product and there is a single price at any particular time. So, only one price decision you have to take, that okay, what should be the price. Let us say if I consider from Monday to Saturday. So, what can be the price on Monday, what can be the price on Tuesday, P1, P2, P3, P4, P5, P6, on different days of the day, what is the different price, that is denoted by PT, P1, P2, P3, P4, P5, P6, like that. And when you have a particular level of price, that particular level of price on a particular day will create a particular type of demand function which is represented by DTP, that based on that particular price you will have a particular demand function, and this demand function may vary for different prices. At price, it is not that you just change the price and the demand function will remain same. The point which I am trying to say, that let us say there is a demand function 100 plus P. So, now if demand is if P is P1 So, D will be D1. If P is P2, D is D2, like that. That is not the case. The case is that this demand function is changing based on the T value also. So, for P1 on day 1 P1, then here the demand function will be, for example, 100 plus P1, and on day 2 when the price is P2, the demand will be, let us say, minus 50 plus 2P2. So, that means on every day, if there are, let us say, 6 different times, and for 6 different times, on every time there will be a different price P1 to P6, there will be 6 different type of demand rates, because demand rate is a function of time as well as unique price. So, these are the conventions which we are going to follow. Now, we introduce another important convention, that is J, which is a function of time and demand. Now, J is a function of time and demand, which is basically representing marginal revenue, and marginal revenue is basically at this level of on this particular time with this particular demand. If you sell one extra unit, what will be the marginal revenue at that level? So, this is R into TD, and R into TD is basically the revenue multiplied by the demand, and if you take the differentiation of that with respect to D, it will give you the marginal revenue, that is the JTD function. Now, going further, let us try to understand the working of this deterministic model with the help of this example. Now, here we have 2 period selling horizon. Let us say week 1 and week 2. For example, whenever you are holding a particular research conference, in research conference maybe week 1 and week 2 can be the early registration and regular registration. So, these are 2 periods of selling horizon, and we want to keep different pricing for different time horizons. Now, for this first time horizon, our D1, that is going to be the demand of first time horizon, is given by this demand rate 100 minus P1. P1 is the price for first week. D2 is given as 120 minus 2P2. So, these are the demand rates given to us for 2 time horizons. Now, the purchase behavior is myopic. We understood what is myopic, that is the short sighted. Customer is going to see his benefit. Now, for revenue calculations, revenue is price into demand. So, the R1 will be P1 into D1, or you can say P1 into 100 minus P1, because D1 is given as 100 minus P1. R2 will be P2 D2, that is P2 into 120 minus 2P2. Now, going back to your basics, that will give you that R1 is 100 P1 minus P1 square, and for getting the maximized value of this, you have to do the calculation, that is R1 equals to 100 P1 minus P1 square. Do the differentiation of this with respect to P, put that differentiation d by dP of R1 put equals to 0, and when you put this equals to 0, you will solve it as 100 minus 2 P1 equals to 0, and you will get P1 equals to 50. And when you get P1 equals to 50, the corresponding value of D1 will be 100 minus P1, that is 50. So that P1 50 and D1 50 for the maximized revenue in this case. Similarly, for second phase, you have P2 into 120 minus 2 P2, you do the multiplication, do the differentiation of this revenue function with respect to price, put that value equals to 0, and that will come as P2 equals to 30, and when you get P2 equals to 30, so the corresponding value of D2 will be 60, that is P2 is 30 and D2 is 60. So, the maximum demand, if we keep the price equals to 50, in D1 the first time period you need to allocate 50 units, and for the second time period, because in the second time period you already mentioned that customers are more price sensitive, and therefore, in the second time period you are reducing the price from 50 to 30, and therefore, your demand is also increasing from 50 to 60 in the second period. So, first period your revenue is P1 into D1, that is 50 into 50, it becomes 2500. The second period revenue is P2 into D2, that is 30 into 60, 1800. So, the total revenue is coming to be 4300 total revenue. But have you observed one important thing in this? That important thing is that to get maximum revenue of 4300 in this particular case, you should have a total capacity of 110, 50 for first week and 60 for the second week. But as we were talking of constrained supplies, let us try to understand in this way. If capacity is 110, you will get a profit of 4300. If capacity is more than 110, then also the profit is 4300 only. There will be some unused capacity in those weeks. But considering a scenario where capacity is less than 110, capacity if less than 110, then how to distribute your capacity for these two time regions, that is important issue for, and for those capacities what should be the pricing level also. Right now, if let us say if 110 is the capacity, or you can say if there is no capacity constraint, your maximum revenue in this particular case will be 4300, but there is a capacity constraint, and there, so let us see what we will do now. So, the this effect, as I just told you, is coming when we have the capacity of 110, but if capacity is less than 110, the effect of that capacity constraint is going to come on our revenue capabilities. We are considering a case where the capacity is 40. So, now the question is, how are we going to divide the capacity between these two periods? So, here again we are going to write these marginal revenue functions J1D1. If you remember, we have already mentioned that J is TD and T is time. So, J1D1, J2D2, that means the marginal revenue for first and marginal revenue of the second period. So, the marginal revenue equations, how did we develop that? Also we saw that these are developed by doing the differentiation of this particular function r into Td, and we have already seen that how we have done this marginal revenue calculation in our previous discussions. So, I am directly taking these j functions of minus 2d1 plus 100 and j2 for the second period as minus d2 plus 60. Now, I will like to take you to our inventory management classes. In inventory management classes, we discussed that the cost of keeping the inventory will be minimal when in our EOQ models, where we are able to almost match our carrying cost and the ordering cost. Similarly, in this particular case also, when both the periods are giving me almost equal marginal revenues, that is the point of optimization, and therefore, I need to see that the marginal revenue from this particular case and marginal revenue from this particular case are almost equal. So, we will show you with the help of this data that how we are going to allocate the capacity. Capacity is 40 and that we have to allocate between two functions. J1D is minus 2D1 plus 100 minus 2D1 plus 100 and J2D is minus D2 plus 60. So, let us consider a scenario that I am giving these capacities equal. This is let us say 20 and this is also 20. So, if D1 is 20, D2 is 20, your J1D1 marginal revenue here is minus 2D1 plus 100, that is minus 40 plus 100, that is coming to be 60, and J2D2 is again minus D2, that is 20 plus 60, that is 40. So, this calculation will come 60 40. The value of R, this is combination of R1 plus R2. So, for that we know that what is the function of R1 and R2, that is P1 D1 and P2 D2. R1 is P1 D1 and R2 is P2 D2. Now, what is my P1 and what is my P2? For that purpose, let us again go back to this particular equation. D1 equals to 100 minus P1 and D2 equals to 120 minus 2 P2. 100 minus P1 and D2 equals to 120 minus 2 P2. Yes. So, if my D1 is given as 20, so my P1 is 80, D2 is given 20, so 120 minus 2 P2, you will have 2 P2 equals to 100 and P2 equals to 20. So, R1 comes out to be P1, that is 80 into 20, that is 1600. R2 equals to 20 into 20, 400. So, the total revenue will be 2000. Total revenue which you are now getting is 2000. Now, what we have done, which is ready made for you, that we have started adjusting the number of D1 and D2. We are increasing the number of D1, making it 21, make it 19, then 22 and 18, and correspondingly we have, in fact, these two columns may not be immediately needed. Rather, it is better that we have columns of, so for that purpose I request all of you that we can make a table like this: D1, D2, P1, P2, R1, R2 and then R. The calculation which we just initiated, if it is 20, it is 20, P1 will come 80 and P2 will come I think 20. So, R1 is P1 D1, that is 1600, R2 is P2 D2, that is 400 and total R will be 2000. So, this is our initialization of the calculation process. Then make it 21, make it 19, 22, 18, 23, 17, 24, 16, 25, 15, 26, 14, 27, 13. So, in this way you can change the values of D1 and D2 with this constraint that D1 plus D2 is 40. With this constraint you will adjust the values of D1 and D2. I request all of you to complete this table, do the calculations for remaining P1 and P2, and that is also not very difficult because D1 equals to 100 minus P1, 100 minus P1 and D2 is 120 minus 2P2. So, you can put your different values of D1, D2 in these two equations, in these two relations, and correspondingly you will get the values of P1 and P2. For example, if I see that corresponding to 27, value of P1 will be approximately 73 and corresponding to 13 D2, the value of P2 will be 120 minus 13 equals to 2 P2. So, P2 will be 107 by 2, it is around 53.5, and with that you multiply your D1 and P1, you will get R1, you multiply D2 and R2, you will get R2, and then R is D1 in fact R1 plus R2. So, the complete calculation is for your reference, ready reference, is available in this table. We have already done this calculation for you, and here you see the different values of R as we are changing the combination of D1 and D2. 2634, it is increasing and going up to 2666.5, and when you see this, the D1 is 27, D2 is 13, and here the marginal contribution for two periods, first and second period, not exactly equal, but almost equal. One contribution is 46, another contribution is 47, and this is the maximum revenue. This is the maximum revenue, and this maximum revenue where these two marginal contributions, are almost equal. So, this becomes a kind of a theorem that at the optimal level, the two periods should give you equal contribution. For example, and now how it can be practically used also. For example, if you are able to calculate, if you are not able to calculate the possible revenue for different combinations, but if you are having this type of system where you have divided the capacity between two periods, and you are able to calculate the marginal revenues from these capacity distribution. If these two marginal revenues for two different periods are almost equal, then you see, then you can understand that you have actually divided the capacity for maximum benefit. But if there is a substantial difference between the marginal revenue of two periods, then you can say that there is a scope of improvement. You are away from the marginal thing. You see that as our balance is moving away, here it is 46 and 47, difference of just 1, 46 48, difference of 2, 44 48, difference of 4, 45 50, difference of 5. As you are moving away from your optimal value, the difference of marginal revenue between two is increasing, and therefore, you are moving away from these optimal values. So, you are therefore able to see that the maximum revenue is possible, since you cannot distribute the capacity. Maybe if there is a possibility to divide the capacity in the fractions also, maybe we can have a allocation where both the marginal revenues are exactly same and the difference is 0, and that will be ideally the theoretically maximum possible revenue. But because the practical reason, you cannot go for the decimal distribution of the capacity. So, therefore, these difference of 1-2 unit. So, out of all the differences between the marginal revenues of period 1 and 2, the minimum difference is of 1 unit. That is the allocation for which you are getting the maximum revenue. So, this is how you are going to decide two important things. One is your allocation of capacity for the two periods, and for this allocation what should be the price, that is the second important thing. So, these are the two important things which we have seen, that how in the dynamic pricing, you know that in this case for first period you are keeping a very high price, that is how much, 73 rupees, and you know that when I am going close to the end of the sale, I will further reduce price of 53.5, and I will keep this price of 73. You can understand not exactly in terms of week 1 and week 2. You can understand this in that way also, that I started with 40 in the beginning and I am continuing with the 73 price equals to 73, I am continuing till I use my 27 units, and when I am left with only 13 units, when only 13 are left, I will reduce the price to 53.5, and I will finish all my remaining inventory of 13 units with this lower price of 53.5. So, you must have seen in vegetable markets also, when a fresh vegetable comes in the market in the morning, the price may be higher, but when he sees that okay, now only 1 kg is left or 2 kg is left, whatever the limit he decides, the shop owner, he will reduce the price for finishing all the remaining inventory at that lower price. So, this is the system of dynamic pricing without any replenishment. With this, we come to end of this particular session, and we will continue with some more interesting cases of pricing for revenue maximization in our further session. Thank you very much.